This is Mr. McCord's ICP class, Unit 6, Lab number 3, typically. Types of chemical reactions. So we've now seen 5 types of chemical reactions. We've got synthesis reactions that form just one product, no plus something else. It's just arrow, one product, one chemical. We've got decomposition reactions where we have the opposite of that. We start with one chemical that changes into and breaks into multiple chemicals. So it's just one thing, arrow, and then other stuff. We have combustion reactions where we take something with C's and H's, sometimes O's, react it with O2. That becomes CO2 and H2O every time. No matter how many C's and H's you start with, you just balance it out from there. Single replacement reactions swap one of your elements with another element. So you have an element on its own and a compound made of 2 elements. That single element on its own will kick its way in and kick someone else out of a compound. So you're left with a different element on its own and a new compound of those 2 elements. And finally, double replacement reactions where we have 2 couples, 2 compounds that switch partners. So you have new couples going on. You have new compounds, typically by switching ions, like polyatomic ions. So in this lab, we're going to demonstrate a couple different examples of these different types of reactions. We have 6 stations, so since there are 5 types of chemical reactions, we're going to see one type of chemical reaction twice. Station 1 is a reaction between an acid and a base. We are going to indicate that our base is here using this base indicator. It changes color when our solution is basic. Acids and bases are kind of opposites. So acids will neutralize with bases to make water and some other compound that is neutral. It's not acidic or basic, right? The indicator we are using is colorless. It's clear until it turns basic, where it turns pink. If we get rid of that base by adding an acid, it'll turn back to being clear. So we are going to start with our base. Fill up one of these wells about halfway. Dropper's not doing so well. Okay. I'm going to add my indicator, which should turn pink with a base around, and it does. Right. Then I'm going to add my acid to that to react with the base and to neutralize it back towards being an acid. One more drop. There it goes. Now, acid-base reactions can happen in several different ways. So to figure out what type of reaction this is, we need to look at the chemical reaction equation, where we see this plus this, arrow, and this plus this for our reactants and products. That way we can match up the pattern that the chemicals go through from reactants to products and figure out what's going on. Station 2 is a reaction between aluminum metal, so just basically in this aluminum foil form, and a chemical called copper sulfate. We're just going to add some drops of copper sulfate into our little cup. A little bit more than I'm supposed to, so that way it's a little bit easier to see. Not much happens at first. I've got to kind of scrape these together to really get them to react. The cup has started to warm up a little bit, so whatever's going on is releasing heat. That's a good sign of a chemical reaction. we're also getting this sort of brownish color on the other side of our foil. Okay, so a reaction is going on. Our reaction equation will tell us that this reaction should make aluminum sulfate and copper. This brown stuff is the copper. We've made just copper metal, taking it out of this copper sulfate here, and what's left down here in the liquid is your aluminum sulfate. Station 3 is a reaction between rubbing alcohol, C3H8O, and the oxygen that's already in the air. We're going to use about 10 milliliters of our rubbing alcohol. There. We are going to put it in this flask. Swirl it up real good. If we have a rubber stopper, we can also cap it and shake it. This should be good enough. We want to make sure that there is enough vapor here for the oxygen to react with. Since the oxygen is in the air, it's easier to react with the rubbing alcohol, the C3H8O, that is in the air with it. To kickstart the reaction, we need a lighter. There we go. Although we can't see the products, we make CO2 and H2O from this reaction, and that's seen in our reaction equation. Station 4 is a reaction between potassium iodide, that's this Ki, and lead nitrate, which is this PbNO3 2. We're just going to put some together in this well plate. A couple drops in there. Both of them are pretty clear. This has a little bit of a yellow tint to it. When we add them together, we get an extremely strong yellow color. This is actually a solid floating around in the liquid. The liquid left over that reacts is potassium nitrate, KNO3. And our solid stuff, our yellow stuff in here, is lead iodide, PbI2. Station 5 is a reaction between iron metal and the oxygen that's in the air already. To get this reaction to go, we're going to get this up in the air and use a lighter. Now this reaction really demonstrates why it's important to look at the reaction equation, because with the lighter involved and with the way this looks, you would almost certainly guess this is a combustion reaction. After all, there's O2 involved also. However, if you look at the reaction equation, we don't have any C's or H's here. So this can't be a combustion reaction. So be careful on what you pick for your reaction type. What we end up making from this reaction, a little bit darker in color than what we started with. We start with iron, Fe, and O2, oxygen from the air, and we get Fe2O3, iron oxide, or more specifically, iron Roman numeral 3 oxide. Station 6 only has one reactant. It's water. Now, I'm using salt water for a reason I will explain soon. We're going to put a little bit in this cup here. And this is not just an ordinary cup. It has metal tacks in the bottom. All right. We are going to touch the ends of a battery to those metal tacks so that we can conduct electricity through this water. Now, water alone doesn't actually conduct electricity that well. We get electricity to conduct through water with minerals, with salt and other ions that are floating around in there. So in this case, we're using salt water to just help conduct that electricity. The salt does nothing to the reaction itself. So by giving a little bit of energy to the water that's in here through means of this battery, we get a reaction here. Let's see if I can get it closer to the camera. We've got some bubbling there. So we are releasing a gas. The two products of this reaction should be H2 and O2. Should make hydrogen gas and oxygen gas. Now we're not seeing the oxygen gas because it is immediately reacting and rusting the other tach that doesn't have bubbles coming out of it. If we let this run for long enough, we'll start to see the effect of the rusting as our water is going to start changing colors. It's already starting to get a little bit green. And if you noticed, since I flipped the battery, my hydrogen gas is coming out the other side. Now the other tach on this side is starting to corrode. Flip it again. Yeah, we got a big chunk of corrosion just came off right there. Water is definitely getting a little nasty. So that's a sign that our oxygen is there and it's reacting with the metal in one of those tachs. Now in these 6 stations, you probably recognized a couple reactions that I demonstrated throughout the year, or maybe you saw in a different lab. Now we can actually figure out what's going on in that reaction. What type of chemical reaction is going on? What do we start with? What chemicals are there? And what do we change them into by rearranging their atoms? So this is the purpose of all of the buildup we've been doing through understanding what elements are made of and how they bond or how they form compounds with each other, and how they might prefer to make different compounds in different situations. We also learned how to give them names so we can describe the chemicals that we work with, that we start with or break down into other new chemicals that have their own names, that we can distinguish between them. So all of this has led up to basically describing chemical reactions.